right, let's look at this problem called serialize and deserialize a BST. Let's have a read. Serialization is converting a data structure object into a sequence of bits so that it can be stored in a file or memory buffer or transmitted across a network connection link to be reconstructed later in the same or another computer environment. It's design an algorithm to serialize and deserialize a binary search tree. There is no restriction on how your serialization deserialization algorithm should work. You need to ensure that a binary search tree can be serialized to a string, and this string can be deserialized to the original tree structure. The encoded string should be as compact as possible. So our ask is that, hey, try and keep the encoded string as compact as possible. And this is the binary search tree example. Now, a similar question could be asked for just any regular binary tree. Like, how does BST change this thing, or BST is like a subset of a binary tree. If we could do it for a binary tree, then we could do it for binary search tree. But the fact that it is a BST, does it allow us to have the encoded string to be more compact? That's the question. And the answer is yes, because for a binary search tree, you have an additional property that tells you that everything on the left of me should be smaller than me, and everything on the right of me should be greater than me. And because of that property, you do not need to save the entire structure when serializing, like adding those null nodes. So let me take a look at an example. And so I'll switch to whiteboard. And let's take a look at maybe a maybe a tree which looks something like this. So, and I'm trying to build a BST here. It's not a regular binary tree, but like a special case, which is a binary search tree. Let's say its root is maybe 5, and then so everything on the left will be smaller. So let's take something like this. Everything on the right will be greater. So let's take something like 14, maybe 8 here, maybe 10 here. Everything has to be greater. So let's say 20, and on the left, let's say 17 and 18. Let's say this is our binary search tree. Now, if we were to serialize this and not considering it as a BST, then the problem is because of this skewed nature, uh, to be able to serialize, you might have to save all those different null nodes, right? Like this guy's right is null, this guy's right is null, this is null, null. You might have to save all of those extra information as well. For each and every leaf node, we have to save uh, our, a null, some indication for that null to be able to build that entire structure. But we do not need to do that for a BST. For a BST, uh, we could potentially just save the pre-ordered traversal. So let's do the pre-order. So one of the things on BST is the in order is always sorted, right? So in order, we can quickly write the in order of this. It will just be 2, 3, 4, 5, 8, 10, 14, 17, 18, and 20. That's the in order. And in order writing is easy. It's always sorted. So in order is always sorted. The real question is, and this is maybe some other problem as well, which is, uh, can you build BST from its pre-order traversal? Right, that's the real question. So let's write the pre-order of this tree. So pre-order is root and then left and then right, right? That's the case. So the pre-order is you start with 5 and then on you go to left. So you go 4, 3, 2. Then you go to the right. You go 14 and then 8, 10. And then you go to 20 and then 17 and then 18. Now the question is, first let's confirm whether pre-order is correct. So 5, 4, 3, 2, 14, 8, 10, 20, 17, 18. Yeah. Now, given just this pre-order traversal, can we construct the binary search tree? Right? We have not saved the shape, the exact information about null and everything, just the null, null, just the null nodes. That's where the space efficiency or the compact string as compact as possible comes in. So let's try and build the BST. Obviously, the first guy would be this, right? So pre-order is root and then left and then right. So we'll go through the pre-order one by one. Root is 5. Now I want to get my left child. So for left child, the one thing that we have to ensure that for 5's left child has to be less than 5. Anytime something becomes greater than 5, it's not my left child anymore. It's not in the left subtree anymore, right? And that we can clearly see. So at when we reach 14, we will say, hey, this is not my part of my left subtree. So from 5 we go to 4. So for it is less, which is good. So 4. Now we want to build 4's left child, right? And we go to the 4 left child, we try and build it, and 3 is lesser than 4, which is good. Now we try to build the left child of 3, which is 2. Now we'll try and build the left child of 2, right? We'll try and build the left child of 2, correct? And when we try and build the left child of 2, we see, hey, I am at 14. And since I am at 14, and my left child of 2 has to be smaller than 2, that means it's null, right? And then I come to the right child. And when a right child also, we will always pass in the limits, right? So for 5 there was no limit, but for after when you go down there was a limit from minus infinity to 5, right? And there you have a limit for the left child, you had a limit from minus infinity to 3. Similarly for 2's right child, there is a limit from uh, 3, right? Ultimately when you reach here, the limit for the left child is minus infinity to 2. Limit for the right child is only from 2 to 3. And you're at 14, so you can't be greater than this. So if you keep passing down those limits, you will know. So for 3's right child has to be less than 4. 14 is not less than 4. So this is also null. Then you come to 4. 4's right child has to be less than 5. And 14 is not less than 5. So you go to here. And now you are trying to build 5's right child. And 14 is greater than, so you go to 14, right? And now you try and build the left child of 14. You move your index now again. 14's left child is 8. Try and build the left child of 8, which can be between minus infinity, not minus infinity now, which has to be between 5 and 8. That's the range now. And you are at 10. And you are at 10, so it does not fit in that range, so we move. Now we try and build the right child. Right child, what is the range of right child? Well, the right child range is 8 to 14, right? And 10 is between 8 to 14, so you can be the right child. Now we try and build the left and right child of 10. What will the range? For the range for the left child would be, it has to be greater than 8 and it has to be less than 10. But we are at 20, so it does not meet that condition. What will the criteria for the right child? Well, right child has to be greater than 10, but it has to be less than 14, right? So between 10 to 14, but it's just 20. So even this does not meet the condition. And similarly, we'll build 20, and then with the same logic, we'll go to 17. 17's left child, 18 won't meet the criteria. It will meet for the criteria for the right child. And at the end, nothing more is left. So this would be my tree, right? So essentially, the tree that gets built is 5, 4, 3, 2, and then you go 14, 8, 10, and then you go 20, 17, 18, which does match the tree that we had initially. So the bottom line is, because we have this extra property, we know the structure partly based on the information about what can be in my left child or what is the range of my left child, and we can keep passing down that range recursively, reducing, increasing that range, or specifically giving a range for every node that will tell you whether or not a specific node that I'm on right now fits into my tree or not. So let's build the logic based on this information. All right, so we go to the code. So what we're essentially doing is just saving the pre-order for serialization and just building the binary search tree back based on the serialized string. So this is serialization. So we have to separate the nodes by some delimiter. Let's say we use comma for as a delimiter. So we'll use a string builder to begin with, and what we can do is we can pass this to maybe some other helper function. We're essentially doing a pre-order traversal, right? So we do pre-order, we pass the root and we pass the string, and at the end we'll return string builder dot to string, right? And let's write this helper function pre-order. So we are doing a void, we're doing a pre-order traversal in which I have a tree node called root and I have a string builder tree. Now, what am I doing? Well, first thing is if root is null, then I can't do anything. If root is not null, then I want to add root. So now I want to also add delimiter. So um, if this is the first guy, then I don't add a comma. But if it's not the first guy, then I add a comma. So if this is not 0, then I will add a comma, a delimiter before adding it. And if it's the first guy, then you don't need a comma at the beginning, right? So that's fine. And now you're gonna append the value of the node. So root.val, and now you're gonna call this for left and right child. So root.left sp, and that is it, right? So this is just you do serialization. And when you do deserialize, you'll have this data. Well, it could be possible that the tree did not have any nodes. Is that a possibility? The number of nodes can be 0, in which case the string would just be an empty string. So let's handle that corner case. So if data dot equals this, or if data is null, handle that as well. Or if either of those two cases, well, we are serializing, and we are never returning string as null. They're always maybe return an empty string, so we can ignore that case. But if it's an empty string, we can return null. And if that's not the case, then let's write another variant of the same pre-order traversal. So pre-order, we pass this data. We have to keep an index, and that index will keep shifting. So we can initialize that index outside maybe. So we'll do here, and every time you start your deserialization, you'll initialize it to 0 back. So index is 0, so you just do pre-order data. I think that's it, right? Is that really? Yeah. So now the real logic would be in how we do this pre-order. So let's do. So now we are returning a node. Uh, do we pass string or do we pass a different node? So let's split it based on the delimiter, right? Remove the commas and everything. So let's do string array. Let's call it nodes maybe. Yeah, nodes equals to. So whatever data it is, we will split based on the delimiter that we used, and maybe we'll pass this nodes instead. So we're passing this string array now. And one thing would be if my index is greater than or equals to the node.length, that means my entire string is done. I can just return null. If that's not the case, then I have to consider the first guy. Now, but there is another thing, right? We talked about passing on the limits. So we'll pass on those limits here. So for the first guy, there is no limit. So it can be between the minimum and the maximum value. All right. So let's do min and max. We pass these limits here. And now what I'm going to do is, well, is the current node falling within these limits? If it is, then you return that. Otherwise, that's not the path. Otherwise, you terminate that and move to the next right child or something like that, right? So let's get the val first. So value is integer dot parseInt nodes of current index dot val. If this value lies within the range, so if value is greater than min and less than the max, then I'm happy. So then let's call it root equals to new node, new tree node with this value. And I will also return this root. And before that, I'll build the left and right as well. So root.left equals to, and so now I've considered this node, then I will increment the index and I'll do recursively for left and right. So now for the left child, what will be the min? That's the interesting bit, right? So the left child min will be this, but the max will be bound by this guy's value, right? And root.right equals to reorder nodes. Now minimum will be starting from this and will this max, right? That's how your window of the range will keep reducing, and we return root. And that's if that's not the case, well then in that case we'll return null, right? And I think that is it. Okay, let's run. We get some error. Let's fix that. Some spelling mistake, line number 34. All right, run. Another error. Let's try and fix that. I think it's a problem here. There's no value. Nodes is a string array, and so we're just getting the string at that index. All right, the two test cases passed. Let's submit. And it works. All right.